Okay, good morning, everyone. Sorry for being late. I lost track of time. Questions? What questions you guys have? Any questions? Okay. Before I start, a comment about the quiz as usual. I comment about the problem that there were issue in a way. I felt that something was not clear. All right, somehow I had issue with two questions from the quiz. The one that has to deal with graph. So that was the graph you have. And first, one of the question is, what's the limit as x become close to 4 of f of x? Okay, some students have some kind of difficulties with that. Now this was 4 on the picture, and this is the point. Now, when we looking for the limit as x goes to 4, we don't care what happened at the point 4. So this is open, but we actually don't care. It means f of 4 is not defined, but the limit only worries about what's happening close to 4. That's really what we care about, from both left and right. So in this case, whether it's from the left or from the right, the output value are getting close to 2, so this is equal to 2. Even if f of 4 is not defined, it doesn't really matter that much. Now, another question also you had some difficulty with is the limit as x become close to 2 of f of x. Okay. All right. For the limit, let's see what's happening at 2. The value at 2 is -1. From the left, the output are becoming close to -1. And from the right, the output is getting close to -5. In this case, we say that the limit does not exist. So for the limit to exist, the output has to become close to the same value at the point. They have, in a way, to somehow to meet. So this does not exist, because limit from the left different from the limit from the right. And that's crucial. From the right. Okay, so these are the two questions, the graphical question that you guys had difficulties with. So please read the feedback I give you for that. The other one that some students struggled with was the algebraic one. And when I say find the limit algebraically, it means I don't want you just to, you can pick up your calculator and take values close to 2 just to check your work, not to show me the work. Okay, so algebraically, it means you have to really analyze the expression. Now, when we find the limit, as we said before, we look at the denominator here first. Okay, we have a problem. If the denominator goes to 0, we have a problem. But watch here, when x becomes close to 0, the denominator becomes close to 4 plus 20, plus 10, minus 3. So this would give me 11. So the denominator becomes taking value close to 11. Now the numerator is taking value close to 0. So it means I have numbers close to 0, so number close to 11. But this is really 0, pure and simple. It's not indefined, it's not indeterminate. It's 0 over something, which is not 0. So for 11, that's really a 0. All right? Okay. Any questions? All right, please, I urge you to look at the feedback and ask me questions if you don't really answer. All right, since we're talking about graphs and stuff, so let me do one of the problems in the book. So I will pick 16. Okay. Yeah, it doesn't really matter. All right. I should have drawn the picture myself. All right. So number 16, it's just graphical problem, just to make sure we can answer the graph really correctly. So this is here. use the graph of this function to determine the limit as x become close to -1 of f of x. Okay, so as x becoming close to -1, we have to know what happened to x. All right, so what do you guys can say? So this is -1 right there. So when x becoming close to -1, we have definitely to study the limit from the left and from the right. So in this scenario, if we approach this from the left, the output seems to grow very negatively large. The output negatively large, it means the limit, we're comfortable to say it's -infinity. Very good. Now, what about the limit as x goes to 3 of f of x? Does it exist? I mean, is it, what can you say? So it's a 3 for you. And from the left, from the right, you analyze it. And in this simple scenario, it's +infinity. Okay. Now, suppose I take number seven, and I ask you about the limit as x become close to 2. Okay, number 7, what's the limit as x get close to 2? What would be your answer? Okay, I'm looking at number 7. This case, it doesn't exist. Okay, it's not +infinity, it's not -infinity, because it depends where you approach it. If you're gonna approach it from the left, so it's gonna go to +infinity. From the right, it's going to -infinity. In this case, the limit doesn't exist. All right? Okay. Right, so now we keep a little bit along the same line, infinite limit. And I like to define formally what's an asymptote. So vertical asymptote, which are those lines that we're seeing. So let's define it a little bit in a more formal way. So vertical asymptote. Okay. So those lines that we keep drawing, so this line here. So suppose I have this vertical line. Since it's a vertical line, the equation of this line is x equal to a. So these are vertical, then that's for that equation. So we say that x equal to a is called a vertical asymptote. So what's the definition of a vertical asymptote? A vertical asymptote if the following happen. So it's called a vertical asymptote if near this point, near x equal to a, the output value goes to infinity. So let's make this precise. If the limit, when x become close to a, from the positive of f of x is either plus or minus, both are accepted, or if the limit as x become close, f of x is plus or minus infinity. So a line, a vertical line, is said to be an asymptote if next to the point, so when x become close from either side, the output goes to infinity. So that's really the picture. So then that's really the definition for it. Okay. So the question is how to find the vertical asymptote. Okay, so that's the definition of it. Now, if they give us a graph, okay, we know how to really spot them. But if we have a formula, how do we actually find the vertical asymptote? So the question is how to find vertical asymptote. Okay, now, how to find them? First, let's analyze what they are. Vertical asymptote are those values of a so that the function goes to infinity when x becomes close to a. So let us think, if you have a function, what can cause the function to go to infinity? So let me make a little bit the scenario more precise. Suppose my function is the ratio of two functions. It means one divided by another. Okay? And what can cause the function to go to infinity? So what cause f of x to go to infinity when x become close? Let's take a number just to make things simple. What can cause this? So suppose a function is a ratio, so it's one over another. What do you think can really cause the function to go to infinity when x, let's say, close to 2, for example? Any idea? So we've been getting those infinity. What's really causing it? Think a little bit. How were we getting those infinity? Yes, John, it isn't, but what caused this asymptote? What should happen here for the function to go to infinity when x is close to 2? What should happen?
One of them should equal 0.
Right. What should happen is that, not one of them, g of x. Yeah. What should happen is that the denominator should become close to 0 in a way. Okay, so when g of x become close to 0, when x become close to 2, in general, the function will go to infinity. So what caused the vertical asymptote are the values of x that make the denominator go to 0. Now, there is one issue, is that we want those that make the denominator go to 0, but we don't want the numerator to go to 0, because as we've seen before, if we have small over small, it's not plus infinity. But our guidelines, and then we check everything, our guidelines is to find the vertical asymptote usually, and I'll put usually in code because, so to find the vertical asymptote, usually, and I will explain in a problem where I put in usually, we find the value of x. We find the values of x that makes the denominator 0, and then we check. That makes the denominator 0. So that's usually, intuitively, the case. That makes the denominator 0. And then we check. We check if actually the function goes to infinity, and then we check our answer. Okay, so the vertical asymptote, it means they occur when the function go to infinity. But when does the function go to infinity? Really when the denominator have become very, very small, but granting the numerator doesn't. So let us immediately take up examples. Okay, so for example, okay, so example 1, a very simple example, and let me take f of x to be 1 over x minus 1. Okay, and the question is find the vertical asymptote. Okay, so let's do that. Please, if I'm going fast or you cannot write things down, make sure to put on chat. All right, don't shy away. So question is find the vertical asymptote. So we use VA to stand for vertical asymptote. All right, as I said a minute ago, the vertical asymptote are, to find them, we actually look for the value of x that makes the denominator equal to 0. So we're gonna do that. So x minus 1 equal to 0, it means x equal to 1. So we expect the issue to happen at 1. But now we have to check our answer. What does it mean to check our answer? What does it mean to check? We have actually to make sure that it's correct. It means when x becomes close to 1, the function is actually going to plus or minus infinity. So the way we check it, we have to check in this case actually to positive, sorry, what happened when x become close to 1 from the negative, and the other one from the left and from the right. All right, let's see good practice for those. So now let us analyze it. When x become close to 1 from the minus, this is 1 over x minus 1. Okay, so at 1 we know it's not defined. So now the question is, what's happening next to 1? That's really what I'm really after. All right, when x become close to 1 from the negative, what's going to be the limit? So let us analyze. 1 from the negative, it means tiny bit less than 1. So you're talking about 0.99. So 0.99, point minus 1, that's going to give me small negative. Okay, but I have 1 over small negative. 1 over minus 0.0001, that's a large, so this is equal to minus infinity. So now I'm sure it is in asymptote because the function is blowing up. So now I feel comfortable drawing my dashed line here. And I actually know a little bit. I know that when x becomes close to 1 from the negative, the function is like that. Okay, so I already know a little bit of the graph of the function, which is important, absolutely. Now when x becomes close to 1 from the positive, so I need the limit of 1 over x minus 1. Now x is tiny bit larger than 1. So I'm thinking about 1.1, 1.01. This is small positive. The limit is plus infinity because I have 1 over small. So this gives me another hint how to graph this function. Okay, so that's really at least near 1. That's how the behavior, and x equal to 1 is actually an asymptote. So x equal to 1 is an asymptote. Sorry, a vertical asymptote because the function actually blew up to that. Okay, so we're going to do 2 more examples along the line. So example number 2. Okay, before I make up the function, I write it, I actually would like to ask you the question. And then I write the problem with you. So don't write anything, just think a little bit. Suppose I want to create, and I feel like doing the following. I want to create a function that has an asymptote here at minus 1. And I wanted to have an asymptote at 3. Okay, as I said, you don't have to write, I want to make up the function yourself. All right, so I want the function to have asymptote here and here. Who can give me a formula for the function? Let's make up a formula that you think will do the job. Elizabeth has an idea? Anybody else? Where is it? Where did Elizabeth came with her answer from? So she's giving me x squared minus 2x minus 3. Where do you think she came up with her answer from? Right, what she did is, okay, I want an asymptote at minus 1, so she said, okay, I want the denominator to be 0 at minus 1. So she put x plus 1 because at minus 1 it will be 0. And then she said, I want it to be 0 here, so she took x minus 3. All right, and then she multiplied them out, giving her x squared minus 2x minus 3. Okay, so this is really the idea. So now now that we found the function, what I'm gonna do is I'm gonna take this function here, and that's gonna be my example 2. So the one that you guys discovered, my example 2, and I'm gonna analyze it with you. Okay, so example number 2 is going to be the following function. 1 over x squared minus 2x minus 3. And the question is find the vertical asymptote, study the behavior near them, and that's it. So find the vertical asymptote. So and check your work. When I say check your work, it means you have to really convince me that if you tell me x equal to 1 is an asymptote, you have to convince me that the limit when x goes to 1 of the function is plus or minus infinity. You have to convince me of that. And you'll see a reason in a second. So find the vertical asymptote. So the step one, we ask ourselves, one is the denominator equal to 0? But that's where they are more likely to occur. So now how to solve this? We factor. So I'm moving backward now. 3, 1, x minus plus. So this will give me x equal to 3 and x equal minus 1. Okay, so these are the candidates. Now let us check each one of them. So I need to check the behavior near each one of them. So I have to compute the limit as x becomes close to 3 from the minus of the function. Okay, that's is equal to 1. All right. So this is my 3 here. And I'm like approaching x from the negative, so it's a little bit less than 3. So 2.9, 2.99. Now, if I want to do it algebraically, and I'm going to plug in 2.99 here, it's a little bit nasty to do the math. So one way to go around it, to make the math much easier, is actually to factor out. And you will see in a minute why factoring, so I'm moving backward, is much easier. So if the function is given to you this way, finding this algebraically, if we factor out, it will be easier to analyze. Now, why it is easy to analyze? Because now, when x becomes close to 3 from the negative, this will become close to 4. So that's easy. I don't have to plug in. And when x becomes close to 3 from the negative, so that's 2.99. So this will be becoming small and negatively small. So now I have 1 over 4 times something small but negative. So I will have a small negative in the denominator. So this whole thing will go to minus infinity. So factoring will make a little bit the analysis easier. All right, so I'm ready to start graphing here. This is my 3. And from the left, I am right here. That's really already a good chunk of a piece chunk. So now I study the limit when x becomes close to 3 from the positive. And again, as we realize, we're going to factor the denominator because the analysis will be way easier. So I will have 1 over x minus 3, x plus 1. And now when x is larger than 3, this is always close to 4. It's a small and it's positive. So this would give me plus infinity. So when we're getting close here, that's what's happening. And x equal to 3 is definitely a vertical asymptote. Now I want to check x equal minus 1. And this one, I want all of you on a piece of paper, analyze this. I don't want to do it myself. Eventually I'll do it. I want you to analyze. I want you to analyze this limit. And x squared minus 2x minus 3. So I'll give you a minute to analyze it. Is it plus infinity? Is it minus infinity? Is it, I don't know what. Okay, try to imitate what I did because this will make computing, in this case, computing the limit slightly easier. Please, every one of you do it. Every one of you do it. I can't see you, but I have to trust you. Anybody? The limit is approaching plus infinity. Agree? Everybody agree? Okay, since I didn't do the problem myself, I will have to hold on and do it. Alexander, what do you think? So, it's going to give me 1 over x minus 3 x plus 1. Okay, and then I start my analysis. When x become close to minus 1, this basically close to minus 4, no problem. What about this one? X become close to minus 1, so this is minus 1 from the positive, right there. It means it's minus 0.99, something like that. So minus 0.99 plus 1, so this is going to give me small positive, right? So why are we getting plus infinity? What's happening here? So it's becoming close to minus 4. I'm right. And this is small positive. Am I right? Yes. So the whole thing is what? Is it small positive or small negative? The whole thing is small negative. So this is going to be minus infinity. All right, so it's not going to be plus, it's going to be minus infinity. So usually all of your answer are fine. So I had to double check myself. So this is minus 1, so I am down here. That's what's happening. Okay, so let's do the last piece. When x become close to minus 1 from the negative, again, what do we expect in this case? So I will put immediately the factored out piece and we analyze. This is not affected. That's always minus 4. And now here, minus 1 from the negative. So it's in my mind, this is minus 1. We are a little bit less than minus 1. So minus 1.1, minus 1.2. So minus 1.1 plus 1, so that's going to be a small negative. So minus 0.001. So I have minus minus, that's a plus infinity. And the limit is going to be plus infinity. Okay, and I'll slow down just to make sure you guys are with me. So this tells me that definitely x equal minus 1 is a vertical asymptote. I have really no doubt about that. It's a vertical asymptote. And according to the graph will tell me that at this stage, my function is going to go like that. Okay. All right, one last example to deal with this idea. And it's the following. Right? So when I said it is vertical asymptote, usually, and I made sure to tell you, usually when the denominator equal to 0. And it's not usually like states most of the time. But there are some odd cases. So remember I told you usually we find. There are some cases, but I have to address them when the denominator equal to 0, we don't actually have an asymptote. And this will occur usually when the numerator go to 0. So let's make up a scenario and do that. So let me take the following example. Suppose I take the following function, f of x equal x plus 1 over x squared And I did that on purpose to show you what's really happening. All right, this is my function. So as you realize, I kept the same denominator as the previous one. I did not really change it, but now I manipulated the numerator a little bit. All right, and the question is find the vertical asymptote and check your work. That's really the question. All right, our approach is as usual. We look for the value that makes the denominator 0. So that's what we look. So x squared minus 2x minus 3 equal to 0. And since I did this a minute ago, it means x equal minus 1 and x equal to 3. Okay, and now we check. We always check. So let's check near what's happening near 3. And I'll try to do that faster this time. So what's happening near 3? So we do it from both sides over. Because I have the square, it's easier to analyze if we factor, and I think you should guys see exactly what's really happening right now. So when x becomes close to 3, this is becoming, of course, we can simplify this. I'm not really, so this is basically the limit of 1 over x minus 3 as x becomes close to 3 from the negative, because I can simplify by x plus 1. And now 3 from the negative, it means this is my 3, 2.9 minus that. So this is going to become small negative. This is going to become minus infinity. So I definitely have an issue, an asymptote there. Now, when x becomes close to 3 from the positive, I do verbatim the same. And I get positive infinity. So near 3, there is an issue. From the positive, I am here. From the negative, right there. All right? So x equal to 3 is absolutely a vertical asymptote because the function totally blows up. Now x equal to minus 1. That's when the denominator is 0. But what's happening when x is close to minus 1? So I took care of the first case, near 3. And now what's happening near x equal minus 1? So let us see. When x becomes close to minus 1 of the function, what's going on here? When x becomes, let me say from the positive. When x becomes close to minus 1, of course, we know that this is 0. There is no question about it. That's how we got this minus 1. But also this one becoming 0. So that's really the issue that we can sometimes have. So numerator, denominator close to 0. And we know that in this case, the limit can be anything. It doesn't have to be infinity. So to compute this limit, as we did in the previous section, we actually had to factor out and the x plus 1 cancel, and I will have the limit as x goes to minus 1 from the positive 1 over x minus 3, which is going to give me 1 over minus 4. So definitely x equal minus 1 in this particular case is not a vertical asymptote. I will still check from the negative, but at least it doesn't look good. It's not a vertical asymptote, and this is the scenario because the numerator also went to 0. So now, if I compute the limit from the negative of the function, we're also going to get minus 1 over 4. So x equal minus 1 here is not a vertical asymptote. But sometimes not a vertical asymptote. So sometimes this scenario will occur. Okay, so which value of x, basically, for which the value of x that makes the denominator 0 that may fail to be asymptote are those that will also make the numerator 0. But how will this affect the graph though? What's going to happen in the graph in this case? What's going to happen in the graph? So this is minus 1. How do you think it will make a whole exactly. So what's happening here is the following. The function is not defined at -1, period. The denominator is 0, so there is no definition. But from the left and the right, the function is becoming close to -1/4. So it means that the function here somehow is going to approach, now we don't have a good picture. It's going to approach -4. We have a big hole. So this is a hole, big hole here, and then the function may go like that. Okay, that's how it's going to be. And this is that's an open hole, because it looks like not, it looks closed in my notes. That's really an open hole. So the function approach -4 from both sides, and then there is an open hole. Okay, so that's really the picture in this problem. Right, so that's how we take care of the vertical asymptote. They are not really hard to find. We have to check them, and sometimes we have anomalies like this. Questions before we proceed? All right. Okay, so today we're gonna move to the last piece of limits, and this is called infinite limit, limit at infinity, sorry. So we move to that, section 2.5, limits at infinity. Okay, so we start this today and we finish it tomorrow. All right. So I start, you know, what's the idea here? The idea is the following. I start with an example. Suppose I take a function. And let's see what I'm going to take. And I'll just make a function x -1 over 2x plus 4. Okay. Now, we know when this function is not defined at x equal -2. But what we're interested in this particular problem is the following. So this is really what my question is. What happened? So what happened? So this is my function. What I'm interested in is the following. What happened to the output value when my input start getting larger and larger values? So when x start increasing and increasing and increasing and taking like values like 10,000, 1 million, and so on and so forth, the question is, you know, what happened to the output value? Okay, so the big question is, that's the real question, what happened to the values of x, f of x, to the output values, the values of f of x, when x, what we call, goes to infinity? It means, what does mean x goes to infinity? It means when x takes larger and larger positive value. Larger and larger positive value. That's what it means goes to infinity. It starts growing without n. So as x growing, grow without n, what happened to f of x? And sometimes we call this problem the end behavior of f, of the function. So we call this problem end behavior. And behavior, it means what happened, what's the behavior of the function when x is large. All right, so I have no idea. We're gonna make a table at the beginning and start really analyzing. So this is my table. I'm gonna take values of x and I'm gonna look at the output value. So my output values are x -1 over 2x plus 4. And I'm going to start taking values of x larger and larger, and probably I'll need my calculator here, and start figuring out the output value. So, okay, let's take 10, for example. Let's take 100, larger value. Let's take, I don't know, 10,000, and then we see what's really going on. All right, at 100, at 10. What's the output value? 10 minus 1, it's a 9. Over 20 plus 4, 24. So we're gonna a little bit compute to have an idea what's going on. So I'm having 0.375. Okay. Now I'll take x equal 100. So larger value to speed up the process. 100 minus 1, that's a 99. over 200 plus 4, 204. So this is almost equal to 204.485. Okay, so we keep, but my goal now is keep taking larger and larger value and watch what's happening here. When I realize that those outputs are becoming close to a fixed number, that's really when I have to stop. But I have to see what they are getting close to. So now I have 10,000 minus 1, so it's going to give me 9,999. I hope my math is correct now. And then it's going to give me 20,000, right? And 4. So how much are we going to get? And intuitively, what's happening? Okay, divided by 2,000. Oh, how many zeros? 3 zeros. So I'm getting 0.499. Okay. Now I can keep going, of course, forever. So I can take, I took 10,000, I can take 100,000, but I think you are bored with that. And if I compute this, I would get 4999, something like that. All right. So what do you think is actually happening here? As X gets larger and larger, those output are becoming close to what? Okay, everybody tells me they are getting close to 0.5 or a half. Okay, now intuitively it makes sense because if we are careful and if we watch what's really going on here, the numerator is, let's say, 99 in this case, x equal 100. This is 99. And this is 204. So it's like if you're doing math mentally, it's almost like 100 over 200. So this is always twice that much. And this is really happening also the same. So the denominator is almost always almost twice the numerator. Okay, but we'll talk about that in a minute. So we're getting a half. So how are we going to write this mathematically and what's the effect on the graph? So it's fair to say that the limit, that's how we're going to write the limit. As x goes to plus infinity of f of x, so we're going to write the limit, which read when x takes larger and larger values, the output values are becoming closer and closer to that. So we say the limit as x goes to plus infinity of f of x is actually equal to 1/2. And the graph. We always have to understand how this is graphically being affected. So this means the following. This is my fun. I'm not going to graph all of it. Every time I'm graphing a little piece and then slowly we build the whole picture. So this is my function f. When x takes large positives, so x become close to here, my output is becoming close to 1/2. In this particular scenario, realize that it's never equal 1/2, but getting closer. So the way we graph this is that this is a half, and we draw this line right there, and we're gonna call it the horizontal asymptote. We draw this line, and then what's the output value? They are getting close to a half. Now, because I plugged in point, we know that they are less than a half, but close to a half. So my graph is going to look something like that at this stage here. That's how this will affect the graph. Okay? And this line, we will call it a horizontal asymptote. Okay. So the goal of this section is basically how to find those type of limit instead of plugging in values, because we can plug in and we have very good ideas going on, how to find those types of limit algebraically, not only numerically. All right, so before we do that, the last 2 minutes, I always like to do some fairly simple limit. And then when I do the simple limit, and then we do the, which is tiny bit kind of more complicated. So simple limit, very simple limit. Simple limit. Let me ask you to find the following. Find the limit as x goes to infinity of 1 over x. Okay, means, let's watch carefully. When x start taking very, very large value, what happened to 1 over x? Means you take 1, divide by a very large number. What do we get? So if we take the table, x1 over x, I guess all of you see the picture. Okay, so if I take x to be 10, I have 1 over 10. X equal 100, 1 over 100. Okay, 0.01. X equal 1,000, 1 over 1,000, 0.001. So you take 1, just 1, and you divide it by a very, very large number, the ratio is going to be very small number. Okay, so those are very basic, simple limits. So, and it's not only for 1 over x. Suppose I take 1 over, I mean, not all, let's me take 100. Actually, that's nicer. Over x squared. What do you think the limit is going to be? Also 0. Do you agree with him? Does the 100 matter? No, because this is 100, all right, it's relatively large, but x is taking value like 10,000. So you'll have 100 over x keeps growing. So this is fixed. It's 100, but it's really a constant number. It's really a fix. This one can go, it's just go any value you want. So we are again at 0, all right? Now, very simple limit, as I said. What happened the limit of, let us say, very simple, x goes to infinity of x squared. So when x gets very large, x squared, it gets even larger, plus infinity. Finally, let us say what happened to the limit as x goes to infinity of x squared, but let us say I take away 2x from it. So now I'm creating a polynomial in x. And what happened to that when x goes to infinity? So this is large minus large. What's going to happen in this scenario for the limit? Infinity, I'm getting infinity. Do we agree? And really why it is infinity? Okay, this is x goes to infinity. Let us say we plug in 100 in here. Okay, 100, just 100. If I plug in 100, what will I get? I will get 100 squared minus 200. Right, so I plug in x equal 100. So we know very well that x squared grows way, way faster than x. So when I take x squared, I take 100, I'm going to have 10,000, I'm going to take 200 from it. So this is very small relatively to x squared. So this is going to be large. And of course, things get worse. If I take x to be 1,000, you can imagine what we're going to have. 1,000, 1, 1, 1. So if I'm doing, that's 1,000,000 minus 1,000. Very good. That's going to be also large. So what really is going to, I have an expression that's like this. What's really going to take over is the term that grows to infinity faster, the term with the highest degree. And this is going to be equal, of course, to plus infinity. Okay? All right. So these are the simple limits. And tomorrow we start a little bit more complicated limit. Okay? You guys had your review for, sorry about the noise in the background, I can't change it. You have your review for your exam, so please get started. And if you have any questions, let me know. And bye for now.